Good morning, everyone. My name is Shantanu Bag, founder and CEO of AsterTech LLC. And we are developing lightweight, high-efficiency solar power technologies for providing unlimited power anytime, anywhere. And we are doing this by turning any surface into photovoltaic solar panels. Let me give you a brief background of where I am from and why I am interested in this technology. I have a PhD in chemical science from Northwestern University in Illinois. Then I spent around 4 years in IBM research in New York, and then around 4.5 years at Air Force Research Laboratory. I was born and raised in a small village in the eastern part of India, where we did not have any electricity until I was in 3rd grade. So later on, when I was in college, I really felt the need of low-cost solar electricity for those remote village applications. And that brought me here. Over the last 10 years, I have been involved in developing new technologies in the solar energy space. And the technology I'm going to present you today will show how we are not only solving the problems of NASA, but it could be also useful for human beings on the Earth. This is my 7-year-old kid in Philly Science Museum, and the questions it got his attention was, might human beings ever walk on Mars? And he was very excited over the last Memorial Day. Not only sending human beings on Mars, but NASA and other private companies have long-term visions of colonizing Mars and other outer planets. But all these human missions would require enormous amount of electricity for their scientific explorations. And solar would be an possible options for meeting those energy demand. Solar technology is kind of mature technology and very reliable, and it has been also used for different space applications and also different commercials and terrestrial applications as well. And it has been also used on those Mars rovers and landers. But given the distance between Mars and Earth, one of the major challenges these human missions would pose on those travelers would be strain on resources, where rapid and frequent supply and resupply of the capabilities are not possible. So in order to overcome those challenges where we cannot send every time all those supplies to Mars or other planetary surface, so rapid and on-demand manufacturing capabilities are really essential for success of those technologies, where those travelers don't need to rely on the supplies from Earth, but rather they can manufacture whatever they need on like solar cells or other kind of batteries or any kind of technologies right onto the surfaces and can still harvest those energies and can do all those kinds of work. Another important concern is the weight of those structures. So any technology which reduces the mass of any payload, that could significantly enhance the capabilities of any scientific missions. So in order to overcome those challenges, at AsterTech, we are trying to develop some low-cost, highly efficient, and lightweight solar cells using 3D additive manufacturing of very low-cost semiconductor materials. By using this technology, we could turn any kind of surface to solar arrays. So our technology involves layer-by-layer depositions of individual components direct onto the structures, and we can do also on-the-fly module encapsulations of those structures, and that could protect our solar cells from environmental damage. So by using our technology, we could turn any kind of surface to a solar cell. For an example, we could turn these kinds of highly bent surface into the solar cells. Our technology is ink-based, highly flexible, and low cost. And another advantage is we can make any kind of structural integrations using our manufacturing technology. So we have demonstrated the use of this technology by painting this highly flexible solar cells onto this curved hemispherical surface, and also on this flexible paper. And what we got at that time, we got around 5.4% efficiency. Remember, this is very early stage demonstrations of this technology. We have not optimized the process conditions that far, but we are sure with further process optimizations that efficiency could go further up. So by using this additive manufacturing process, we can make very complex structures by using layers of materials, like building a Lego blocks. And the advantage of this technology is, like, we can make solar panels in remote locations. It could be very lightweight, and we could do, as I said, we could do very complex structural integration. So if you have very complex structures, like, we can put the solar panels over there. And another advantage of this process is the materials waste of this manufacturing technology is very low. So if we compare this conventional space solar cells, there we can see those are mainly relied on gallium arsenide-based semiconducting materials, which are usually grown on those highly pure semiconductor surface, thick semiconductor surface, using MOCVD process. And MOCVD process is very complex, sophisticated, and very slow process. And since we are they are trying to, those are grown on this thick semiconductor surface, the specific power of this material, of this technology, is relatively low. So the ways the solar cells are made, so you usually you make solar cells on the glass or any kind of semiconductor surface, and then transfer those individual solar cells on it, secondary substructures, and then do module integrations and encapsulations, and then finally deposit transfer those arrays onto the structures. And that process is kind of lengthy, and use of these multiple layers of layers make this process heavy. So as our technology makes solar cells directly onto the structures, and we can do like on-the-fly encapsulations, so we can get rid of those different layers of those structures, and we can get specific power around 23 kilowatt per kilograms. So by using our technology, we could significantly increase the specific power of the solar cells almost 1 to 2 orders of magnitude. And since this is additive manufacturing, ink-based process, the cost would go significantly lower, almost 2 to 3 orders of magnitude. And we could speed up the whole process significantly. So by using our technology, we have been able to demonstrate almost 15.4% device efficiency very reproducibly on just flat surface. And what it indicates that by introducing a new manufacturing process, we are not sacrificing that much of device efficiency. So our technology could be useful for a variety, for lots of applications. It could be useful for space applications as well as different civilian applications. For an example, here we can direct write those solar cells onto the outer surface of this nano or microsatellites, and we can power those up. And the market here is also huge, around $39 million market is expected over next 5 years. In civilian space, this technology could be used for existing market as well as for niche market applications. For existing market, we could build those building integrated photovoltaics device applications. And for the niche market opportunities, we can use these photovoltaic technologies for powering Internet of Things devices. By using this additive manufacturing approach, we can place our solar cells in a complex structures. Doesn't matter if it's flat Internet of Things devices or curved devices, we can place over there and then charge them up using indoor or outdoor light. So at AsterTech, we are trying to build a strong intellectual property using this technology, and we are hoping to license out this technology to the potential customers. We are trying to build patent applications in this market, solar energy market, where it is estimated to be very high. By 2020, it is estimated to be around $450 million market, and with the growth potentials around 22%. So there are plenty of opportunities for us to invent and then apply our technology for commercializations. Our potential customers would be different kinds of, it would be from space applications, for terrestrial applications. For the space, it could be Boeing, Lockheed Martin, SpaceX. In the terrestrial applications, Solar Frontier, Energy, Solar City, Solar Power. And for Internet of Things device applications, those are like Prime One, AT&T, and Aries, but there are lots of other potential customers out there in the market where we can target. So we are right now in the pre-seed stage. We are looking for around $1.5 million over the next 2 years to develop our technology further. With the help of Air Force Research Laboratory, we have demonstrated our technology to this point. Very highly lightweight solar cells, like curved surface, flat surface, we have demonstrated that. And in partnership, we are trying to continue the partnership with the Air Force Research Laboratory. And in 2018, we want to do complete packaging of our solar cells by using additive manufacturing approach. In 2019 time frame, we'll integrate our solar cells to this small CubeSat, nanosat kind of satellites applications. And further, we want to also integrate our devices to the flexible device applications for Internet of Things. So we are looking for partnership opportunities here where we can do product validations of our technology, and where someone could take our technology and manufactures in bulk, like large scales. And we are also looking for partnership with NASA so that we can understand their requirement and tweak our technologies to some extent so that that could be useful for space applications. We are looking for funding as well for team expansions and technological integrations. So you might be thinking why you are the right team to develop this technology. So I am in this solar research area for almost 10 years. Previously, I worked at IBM Research and worked with multiple joint development programs with specifically some of the solar manufacturers, and I know how to develop the technology and transfer those technology to the manufacturing facilities. So some of those alliance partners would be our potential customers for developing our technology further. In our team, we have Mike Shepard from Purdue University, who is our financial advisors, and he has excellent track record of raising money from different sources. In our team, we have advisory boards from research laboratory, IBM Research, from academia, industry, so different sources. I want to particularly mention Dr. Oki Gunawan at IBM Research. He has excellent facilities for device characterizations, and that is highly valuable for developing our technology further. And also Dr. Mike Darkstock at Air Force Research Laboratory. He has state-of-the-art flexible electronics device applications, so that we want to leverage that things for as we go for defense applications as well. And we have also collaborators from national laboratory and also from universities. So our technology is going to change some of the future devices where those are not possible right now. So we are developing this technology, and this technology could be used for designing new kind of devices, and it could be also useful for space applications. We have the right team, right expertise, and the passions to tackle some future challenges. So if you'd like to take part in these innovations, would like to help us, please come and see me after this talk. Thank you so much for your attention. Any questions?
Yeah, thanks. I just had a question about the specific power value that you gave, the 23 kilowatts per kilogram.
Right.
So that value seems to come from like perovskite solar cells that were made more conventionally, so with semiconductor fabrication methods.
Right.
So yeah, can you maybe comment on how?
Yeah, so that is like traditional perovskite, but here I want to point, we can go beyond that. So that we have not calculated that approach yet, but we can go, at least we can get 23 kilowatt per kilogram, but by using our additive manufacturing approach, we can go beyond that. So that's a good question. So at least we can get that point.
That's an amazingly high number. So
Right.
is that achieved by virtue of avoiding like cover glass? So maybe you're printing directly your encapsulation materials. How do you get to that 23 kilowatts per kilogram?
So one of the ways is like getting rid of the glass substrate. And still in these calculations, we have still the encapsulations on the top. So we have just removed the glass from the bottom.
Okay.
And that goes to that value.
So are you printing the electrical connections at the same time you print the solar cells?
That's an excellent question. That's the future hope for our technology. Means right now we have those different paths. Means we have electrodes, we have solar cells, and we have demonstrated all these layers, but we have not integrated. So that is our next step. And
So you're printing directly on surfaces. How does big changes in thermal performance, or you're in extreme light and stuff and it heats up, you're going to keep it on the surface?
That's a really useful question. We have not addressed that kind of challenges yet. So we have just demonstrated, okay, that we could print those things on those kind of different substrate. But yeah, thermal and other kind of issues we have not addressed that far yet. But it is a kind of excellent questions, and we would love to answer those in futures.
How much power have you generated in your demonstrations?
So these demonstrations, 15.4 efficiency, and we have not integrated that kind of module kind of integration. So it's kind of just like
Watts or
No.
milliwatts? Or
How big,
Right
is
now
the,
in
how
the-
big is the cell? We can do the math.
yeah, 15.4%, so 1, and we have done almost, how much, almost 10, it's in the micro,
No, it's milliwatts.
it's the milliwatt range. We have not done all integrations, like this is kind of individual cells yet, so we have not done like integrating individual cells to the final structures and make modules.
So your additive manufacturing process, is it a inkjet process or
It's the aerosol jet process.
aerosol jet? Okay.
So I have a question. I'm sorry.
No, sorry. I was just going to ask, in terms of terrestrial applications, have you looked at the cost associated with your, I guess you call it on-the-fly manufacturing of painting on an existing roof? And is that can that be made cost efficient and scalable?
Yeah, so it can be scalable, and the cost is right now estimated around $30 US per meter square if we manufacture in US. But some of those parts, if we could outsource, that could be a little bit cheaper. So around 30 to 40, but I would say around 35 US dollars per meter square to make those solar panels. So there are lots of assumptions, but
So the money you're asking for, will that address the wiring?
yeah, right now the money we are asking for just integrations.
Of the integration?
Integrations and packaging. So we are doing like encapsulations of these things, but we want to integrate all these things and to make really module level integrations and then integrate onto the surface. Means right now we have just individual cells, but we want to integrate those to the module level with electrodes and other kind of circuits so that we can demonstrate that in further. So it's kind of more integrations and packaging.
What size of cells are you interested in producing, or do you think you're capable of producing?
So right now we made almost 1 by 1 millimeter each cells. 1 by 1 millimeter is 1 by 1 inch actually. So we have demonstrated 1 by 1 inch.
And how big do you think you should go, or what's
So-
your plan?
So with the capability we have, we got around 10 inch by 2 inch substrate. We have demonstrated that reproducibly, but we have not done far beyond that. This is not like, I cannot say it's not possible, it's possible, but we have not that much of manpower to do all these kinds of things. It's kind of automated, but we have not done this. It takes time. The instrument we have right now, it takes a little bit of more time.
So 1 by 1 is so small, 1 by 1 millimeter square is so small that NREL wouldn't even test that. But I'd like to
1 by,
So I'd like to comment on your gallium arsenide cell that you showed there. Typically, people would be lifting off, doing epitaxial liftoff, and
yeah, right.
have
So
that.
that's the,
And so there's multiple companies.
They are
so
doing-
your
yeah, I am aware of that
gravimetric
things.
power
And then-
density number is
And
gallium
whatever I got from
arsenide is,
literature, the power density using this lift-off process is 1.5 kilowatt per kilograms. So the traditional is like almost 0.3, but using the lift-off, that is like some small companies are doing in Silicon Valley and other
well,
areas.
some of that stuff is the copper that they put in the back. So
Yeah, so
you still
that,
need the metallization. Everybody needs metallization in the back. So I'd like to see how you arrived at your 23 kilowatt per kilogram number.
that number is just just removing the glass substrate and also reducing the thickness of the,
And no metal in the back.
no, still we have,
Oh.
still we have the metals.
So is this cell one-sided contact? Is it both sides or single-side contact?
One side contact. So means one side metal contact, when the other side we have the transparent conductors.
So perovskite is a pretty crowded field, right?
Right.
Of research. What is the, and you have a vision for how you want to utilize those materials in
Yeah,
a
so the-
fashion. What is your special sauce beyond the vision, and like how do you protect your position? Like,
So here,
property.
the materials are there, is not like new for our
Yeah.
sauce, but our thing is like, we are the first for doing additive, 3D additive manufacturing and trying to get that materials and print on any kind of substrate.
Do you have
And this-
protection in that?
yeah, we have the IP on that. We have several.
Do you have a sense of how stable these materials are, or how rapidly the cells will degrade in performance?
So those materials without encapsulation, they degrade very fast. But with the encapsulation, they are stable almost like,
Is the
couple of-
encapsulation then included in the 23 kilowatts per kilogram estimate?
yeah, the top encapsulation is included, but not on the bottom. And we are also doing some other encapsulations where we don't need the glass.
When you deploy these in space, how does that change the encapsulation requirements for you? And then what about rad hardness of the materials?
That's an interesting question. So, the glass, traditional way we can protect from using the glass, but we are also looking at different kinds of encapsulations, like some soft materials with some hard materials, with kind of hybrid materials. But we have not tested whether that would be stable in space, and that's why we are looking for opportunities so that NASA can provide us feedback and we can develop the further of our thing.
I'm a little confused on the microsat or nanosat application.
Right.
So those, systems, there's a premium on space, and if your efficiency is only 15%, they're likely to find better options elsewhere, right?
Yeah, the thing is like here we can make it low cost. So here right now the like price of this each CubeSat is around 50K. So we can reduce down the the price using our technology.
Yeah, but you're not going to make enough power for those satellites.
Means this is our initial demonstration 15%, and there is a means people with the material doesn't have any limitation. Like it can go to around 22%. We are just limited by our processing. That's things. And with the manpower and processing optimizations, that could go beyond like 20%. I'm not going to say it can be achieved like 30% or something like that with single junctions, but with single junctions, it could be achieved 20%.
Is there any potential to utilize local materials on the moon or Mars to make any of these cells?
Yeah, that's a good idea. I mean, I don't know much about what is
You should be
available
the
in
guy
Mars.
with the good ideas, not me.
No,
So are there materials there that could be made into solar cells?
The moon, the Mars, I am not sure. Means what are there, and we can use that the minerals over there and can make the solar panels. But right now we can just get whatever minerals we have from here, the ingredients, and can manufacture over there.
Does anyone in the back have any questions? Thank you.